All right. Welcome to lecture 16 of 124103 Biophysical Principles. This is the second lecture that we're having on heat and temperature. So last time we started the topic by talking about temperature. We defined what temperature is. We defined it as how hot or cold an object feels to the touch. And we've seen the temperature, although it's usually measured in degrees Celsius, the SI or the base unit for temperature is the Kelvin. And so last time we also learned how to convert units from degrees Celsius to Kelvin and vice versa. And last time we also learned that the temperature of a substance or of a material causes the molecules inside it to move, to vibrate. And so because of the movement of the molecules increasing as temperature increases, usually objects expand when they are heated and they contract when they're cooled, except for water, which we've seen to have a peculiar behavior as it cools down and forms ice crystals. So today we will talk about heat and then relate heat to what we learned about temperature. So first we'll describe and explain what heat is. In short, we'll define what heat is, and then we'll learn about a property of the material that's related to heat. And this is called specific heat capacity, or simply it's referred to as specific heat. Then we'll use the concept behind specific heat and the relationship between heat and temperature to solve some problems, to see how the temperature of an object changes when it heats up, for example. We'll also look at another material property called the latent heat, which is related to the object changing phase, for example, from solid to liquid and liquid to gas. And after learning what latent heat is, we'll use it to solve problems involving phase change. Okay, so to begin the definition for heat, we know from experience, or probably from intuition, we know that if we put a hot pot on a ice cold bath of icy water, we know from experience and probably from intuition, we know that the hot liquid inside the hot pot will eventually cool down, right? And also eventually the ice in the cold bath will melt. Okay? And we know that heat, when the hot pot cools down, its temperature will decrease, and for the ice to melt, its temperature would have increased, right? So heat is defined as the transfer of energy across two objects at different temperatures. So that means you have here heat transferring, that's hot pot and cold ice. You have heat or Q. So we use the symbol capital Q to represent heat. Heat is transferred from the hot pot, from the hot object to the cold object. And so heat is defined as the transfer of energy because of a difference in temperature. And we know that eventually the hot pot will cool down and the ice will melt. Meaning heat is usually transferred from hot to cold, and it only is transferred while the two objects have different temperatures. So when the objects have the same temperature, then heat transfer will stop, and we say that the object is in thermal equilibrium. So thermal equilibrium means that the objects have the same temperature, and in such a situation when the temperatures are the same, energy is not transferred, or heat is not transferred between the two objects. Right. So basically, heat is defined as the transfer of energy because of the difference in temperature, and heat is transferred from the hot object, so high temperature meaning hot object, to the low temperature or cold object. Heat also quantifies how much energy is transferred. So we also use heat to measure the amount of energy that is transferred between the hot object to the cold, from the hot object to the cold object. Yeah, so heat can mean two things. It's the transfer of energy, and at the same time, it's how much energy is transferred. It's the amount of energy that's transferred. So we can measure heat. It's measured in terms of joules. So the basic unit or SI unit for heat is the joule, capital J. But maybe we are more familiar, the more common way of measuring heat is the calorie, right? So I think we've heard of the calorie when we usually talk about food. So how much calories this food has, or how much calories our body burns when we exercise. Yeah, so when we say calorie, we're talking about the heat that calories in food. We're talking about the heat that's imparted to our body. And in fact, food manufacturers measure how much calories food have by burning a known amount of food and measuring how much energy is transferred through the burning process. And then they use that value and put it at the back of the label of the food packets. Okay, so calorie is a measure of the amount of heat that is transferred to our body when we consume that food, for example. So calorie is not the standard unit. Joule is the standard unit for heat. So sometimes we also need to convert calories to joules, and this is the conversion factor between calories to joules. 1 calorie, notice there's a small letter C for this calorie. 1 calorie is equal to 4.186 joules. Okay. The calories that we'll see at the back of the food packets have this capital letter C. And if you see calories with a capital letter C, it means 1,000 calories with a small letter C. So it's just a weird way of that people thought of specifying calories. Yeah, just take note that there's a difference of 1,000 going from calories with a small c to calories with a big C. And the food labels give us calories with a big C. And so if you're converting 1 calorie with a big C, the joules, make sure to multiply with 1,000. So 1 calorie with a big C is 4.186 kilojoules, or that will be 4,186 joules for the conversion of 1 calorie with a big C to joules. Okay, so those are the conversion factors between the standard way we measure heat in calories and the basic or the SI unit for heat, which is the joules. Right, so we've seen here, so just to summarize what we've been talking about, so hot objects on a cold object, hot on cold, which are both in contact with each other, heat will transfer from the hot object to the cold object. So there's a transfer of energy from the hot object to the cold object. And the transfer of energy will result to the change in temperature of the object, right? So the hot object will become colder and the cold object will become hotter. And so mathematically, so we can see here from this illustration that heat, Q, is related to a change to the change in temperature, because when energy or heat is transferred from hot to cold, the temperature of the hot object will change, and the temperature of the cold object will change as well. And the relationship between the heat transferred and the change in temperature is given by this equation. Q is equal to M times C times delta T. So Q, this is the amount of heat that is transferred. Okay. And delta T, this is the change in temperature. Change in temperature as a result of heat or energy being transferred from hot to cold. So we measure delta T, I mean, we determine delta T as the final temperature, or T sub F, T subscript F, minus the initial temperature, or T subscript I. M is the mass of the object that is changing temperature, okay, as a result of the heat transfer. Mass of object whose temperature changed. And C is a property of the object or the material called specific heat. So it's a property of the material. All materials have their own specific heats or specific heat capacities. It's a constant number that you can just look up in a table or search in Google. So say, what's the specific heat of iron, or what's the specific heat of silver? So it's a constant number. But let's talk more about the specific heat, because it's a property of the material, and therefore it tells us something about how the temperature of the material changes when heat is being transferred out of the material or into that material. So specific heat, it's a measure of how much energy is needed to change the temperature of 1 kilogram of that material by 1 degree Celsius. So this is the formal definition of specific heat. And this is how the specific heats of different objects are determined. So they usually heat up a material, a 1 kilogram of that material, and measure how much energy it takes to change the temperature of that material by 1 degree Celsius. Okay, and by measuring that energy, they are able to determine the specific heat. It's measured in these units, joules per kilogram per degrees Kelvin, degrees Celsius, or joules per kilogram per Kelvin. And as I've said, it's a property of the material which is constant, so you can just look it up from some table or search it in Google. So it's just a constant number there for a particular material. But practically speaking, specific heat is the resistance of a substance to the change in temperature, meaning the higher the specific heat of the object is, the more it will resist a change in its temperature. Okay? Right, and the lower, of course, the reverse is true. The lower the specific heat, the easier it is to change the temperature of that object. Okay, so for example, looking at this table here, for example, you're shopping for some pots and pans. Okay, and you have a choice between, say, a stainless steel pan, say, for example, stainless steel pan here has a specific heat of, so let's use the specific heat for joules per kilogram per degree Celsius, which is this one, 450 joules per kilogram per degree Celsius for the stainless steel pan. And you're comparing that, for example, to an aluminum pan, which has a specific heat of 900 joules per kilogram per degree Celsius. So if you're shopping and you have this choice between stainless steel pan and aluminum pan, which pan would you choose, or which pan would you prefer? Any thoughts? Yeah, iron or steel. Okay. Yeah. So if you're thinking that you want to cook food as quickly as possible, so you want the pan to heat up as quickly as possible, then you would choose iron or steel, because then iron or steel has the lower specific heat capacity, or lower specific heat. Lower specific heat means that object will change its temperature quickly. So that object will heat up quicker. Steel will heat up quicker than aluminum because steel has a lower specific heat compared to aluminum. Okay. But if you want slow cooking, and you want the pan to heat up gradually and more slowly, then you should go for the aluminum pan, which has a higher specific heat, which means that it will take longer for the aluminum pan to heat up. Okay, right. So so it all depends on the application. Right, so that's the concept behind specific heat. It's quite an important concept to consider when looking at substances or materials. So let's look at this conceptual example. So for example, it takes about 2 minutes to raise the temperature of an iron pot of water to boiling temperature. But it takes less than 1 minute to raise the temperature of the same amount of water in a silver pot. So you have here an iron pot and a silver pot. You want to raise the temperature of the water to boiling temperature. In short, you want to boil water using an iron pot and a silver pot. Okay, it takes 2 minutes to boil the water in the iron pot. It takes less than 1 minute to boil the water in the silver pot. Which one will have a lower specific heat capacity? Is it iron or silver? Yep, good. All right, so the material with a lower specific heat capacity will heat up faster, because lower specific heat capacity means easier to change its temperature. And so the one with the lower specific heat capacity will take a shorter time to boil the water, because the temperature, it will heat up faster, right? So you're right, silver will have a lower specific heat capacity. And if you look at the table, indeed, silver has a smaller value for the specific heat capacity. So different substances, different materials have different specific heat capacities, and it influences how quickly that material's temperature changes as heat is being added to that material. Okay, second conceptual example, 1 gram of water requires 1 calorie of energy to raise the temperature by 1 degree Celsius. Whereas 1 gram of iron requires 1/8 as much energy for the same temperature increase. Okay, so that means water absorbs more heat than iron for the same change in temperature. Yeah, so it's the same amount, 1 gram, same change in temperature, 1 degree Celsius, but different materials, and therefore different amounts of energy, different amounts of heat. So which has a higher specific heat? Is it water or iron? Water. Yeah, I see water in the chat box. Okay, so the higher the specific heat capacity, the more difficult it is to change that material's temperature, and therefore if you want to change that temperature by a certain amount, you need to put in more energy, right? You need to put in more energy to that material that has a higher specific heat capacity if you wanted it to increase its temperature, right? So you're right, water has a higher specific heat capacity compared to iron. Right, so equal masses of different materials will require different quantities of heat to change their temperatures, and that depends on the specific heat of the materials. Okay? So given that the mass is the same and the change in temperature is the same, the higher the specific heat, the more energy is needed in order to change that material's temperature. Right? Good. All right. So now let's look at an example of how we apply that equation. Q is equal to mass times specific heat times the change in temperature. Okay, 30 grams of mercury is cooled from this temperature 280 Kelvin to 100 Kelvin, and the specific heat capacity of, or specific heat of mercury is 140 joules per kilogram per Kelvin. How much heat is transferred during the cooling process? All right. It's always useful to write down what the problem tells us, what information we can get from the problem. So 30 grams, grams is a measure of mass. Therefore, we're given the mass, 30 grams. Grams is not the basic, not the basic unit. So we need to convert this to kilograms, and we'll just going from grams to kilograms, we need to divide by 1,000. Okay. 30 divided by 1,000 will give you 0.03 kilograms. Okay, so there are 1,000 grams in a kilogram. So you're going from 30 grams to kilograms, so you have to divide by 1,000. Okay, it's cooled from 280 Kelvin to 100 Kelvin. So from, that means that's the initial temperature, T subscript I, 280 kelvins. 2 meaning your final temperature, or T subscript F, is 100 kelvins. So from these two temperatures, you can get the change in temperature. Okay. Change in temperature, final minus the initial temperature, you'll have 280 minus 100, 180 Kelvin for the change in temperature. Okay, and then you have the specific heat that's given. C is equal to 140 joules per kilogram per Kelvin. Okay, and you're wanting to find the heat. Heat is capital Q. Right. So looking at the equation here, it's just a matter of directly substituting the values, because we know mass, we know C, specific heat, and we've sorted out the change in temperature. Just make sure that your units are consistent, and that's why we've converted our units to this, the base or SI units. So Q is equal to MC delta T, 0.03 kilograms times 140 joules per kilogram per Kelvin times 180 Kelvin gives you a Q of 756 joules. Right? Cool. Are we happy with the solution for that problem? Good. Great. Okay, good. Right, so we've seen that if we put two objects together, one hot and the other cold, heat will transfer and their temperature will change until they have the same temperature. Okay, and it's the same if we mix liquids together or mix fluids together. So if two objects that are initially at different temperatures are mixed, heat is transferred from the hot object to the cold object, and the temperatures of these objects will change until eventually thermal equilibrium is achieved. Thermal equilibrium again means that the two objects have the same temperature, right? And so the hot object will lose heat. Heat will go from the hot object to the cold object, and therefore the hot object will lose heat, while the cold object will gain heat until their temperatures are the same. So if we put these, so we know this from, maybe we've observed this, we've experienced this, or we know this from intuition, and hopefully these statements make sense. So if we put these statements into a mathematical equation, then we can say that the heat gained by the cold object, it will be equal to the heat lost by the hot object, right? Okay, because two objects at different temperatures, heat will transfer from the hot object to the cold object. The hot object will lose heat, while the cold object will gain heat. Okay, and the amount of heat lost will be equal to the amount of heat gained. So we've seen that heat, so this will be Q of the heat of the cold object. Heat gained by the cold object will be equal to the heat lost by the hot object, right? And we know that Q is equal to mass times specific heat times the change in temperature. So if we write this statement in equation form, the heat gained by the cold object will be equal to the mass of the cold object times the specific heat of the cold object times the change in temperature. So the change in temperature for the cold object, we know that it will cool down. So its final temperature will be bigger than its initial temperature. It's the cold object. Sorry, it's the cold object that will heat up. Okay. It's the cold object that's gaining heat. So on the left side of the equation, which refers to the cold object gaining heat, the final temperature of that cold object will be higher than its initial temperature. And so the change in temperature will be the final temperature, which is the higher temperature, minus the initial temperature of the cold object, which is smaller, lower in the beginning. Okay. And on the right side of the equation, the heat that is lost by the object will be equal to the mass of the hot object times the specific heat of the hot object times the change in temperature of the hot object. Okay. And the hot object loses heat. Therefore, the temperature of that hot object will decrease. Okay. So initially, it will have a higher temperature, which is the temperature subscript hot. in this equation, and its final temperature will be smaller compared to its initial temperature, right? So you have this initial T hot minus the final temperature. Right. Okay. I hope that makes sense. Does that make sense? Before we proceed, just making sure that this this line of the equation makes sense. Okay, good. Right. Okay, so we can see here, usually we know everything. So we can measure the initial temperature of the cold object, and we can also measure the initial temperature of the hot object. The mass of the objects we can measure using a weighing scale. The specific heats of the objects, they're just constant numbers we can look up in the table. So by using this relationship, we can find what the final temperature of these two objects are. Okay, and the final temperature will be the same, right? Because heat will transfer until the temperatures of these two objects will be the same. So if we rearrange this equation to isolate the final temperature of the mixture will then be given by this equation here. Right. Yeah, so we won't expect you to do the rearranging of this equation in this course. So you can just use this final rearranged equation for the final temperature. But yeah, we do expect you to know like to sort out which values to enter in each of these variables in this equation. So you have here the mass of the hot object, the specific heat of the mass, a specific heat of the hot object. So T hot, this is the initial temperature of the hot object or the hot liquid. Okay, so likewise, M cold, that's the mass of the cold object, C cold, specific heat of the cold object, and T cold, that's the initial temperature of the cold object. Okay. Yeah, so the T hot and T cold, those are initial temperatures. The hot and cold objects are mixed. Their temperatures will change until they arrive at this final temperature equilibrium, final equilibrium temperature. At this point, the temperatures of the two objects will be the same. All right. Okay, so this equation, we'll use this in the workshop. The workshop problem has, the workshop worksheet rather, has a problem, which is an example of how we can use this equation. The mastery test that's coming up, mastery test 5, will also have there a problem regarding objects being mixed and finding the final temperature. And so you can also use this equation for that. All right, but so far we've been talking about the temperature of the object changing when heat is being added or taken out of that object. But sometimes adding heat to an object will also cause the phase of that object to change. For example, starting from ice, which is solid. If we heat up ice, we know that the ice will melt, right? And so it will change phase from solid to liquid. Okay? And if we heat up water, okay, then the temperature of that water will initially increase until it reaches boiling point. But then if we keep heating up, that water will boil, and as it boils, liquid is converted to gas, right? So water is converted to steam, and so you have this phase change called evaporation. Yeah, and the reverse can also happen. We can start with steam, the gas form. If we cool down the steam will condense and you have a phase change from gas to liquid. Okay. And if we cool down that liquid, the temperature of the liquid will initially go down, but then eventually that liquid will start to freeze. So you have this phase change of going from liquid to solid as water freezes to ice, right? So we can see there that adding heat to a material can either change its temperature, as we've seen earlier, or it can change the phase of that material. Like it can cause ice to melt, or it can, so you have this melting, or it can cause liquid to evaporate and to gas, so you have this evaporation. So phase change is the phase change of a material is influenced by its property called latent heat. Okay, so latent heat, and we'll talk more about latent heat as a property of the material in the next slide. But we've seen in the previous slide talking about, ice melting to liquid and liquid turning into gas, that when a material changes phase, extra heat or extra energy is required, right, to break the bonds of the material. Okay, so when you melt ice to water, you're going from solid to liquid, you need extra heat in order to melt the ice. And likewise, if you boil water, changing liquid to gas, you'll also need extra heat or extra energy to accomplish that boiling process. And so we can also have this heat being related to the phase change, and that's governed by this, that's given by this equation. Q is equal to plus minus ml. So Q, again, this is the amount of heat. Okay, but this time, instead of amount of heat that will cause a change in temperature, it will be the amount of heat that will cause a phase change. Okay. And phase change is indicated by this latent heat, capital L. Latent heat, capital L. Okay. Again, M is the mass of the object or substance that changes phase. All right, so during phase change, you need this much amount of heat Q in order to accomplish the phase change L in a material with a certain mass M. Okay, the plus and minus sign here, we'll talk about that in a bit. Okay, but L is called the latent heat of the material. Again, it's a property of the material. Every material, just like specific heat, it's a constant number that you can look up in some table or Google search. And there are two kinds of latent heats depending on the kind of phase change. So when you're going from solid to liquid, or the reverse, liquid to solid, we call that latent heat of fusion. Going from solid to liquid or liquid to solid, you'll have the same value for the latent heat. And if you're going from liquid to gas or gas to liquid, we call that latent heat of vaporization. Yeah, and the positive and negative signs here, plus minus means you can either use a positive ml or you use a negative ml. So we can simplify this into two equations. Q is equal to plus ml or Q is equal to minus ml. Okay, so Q is equal to plus ml is used when energy is added or heat is added to the system. And that's the case when you go from liquid to gas, or solid to liquid. So when you're melting or boiling, then you need to put in, or you need to add heat to the material in order to cause it to melt and cause it to boil. And so that's where you'll use the plus ml when heat is being added. Now, if you go the reverse direction, where you're taking out heat, so that means you're freezing or condensing. Okay, so in condensing, heat is taken out of the steam, and therefore it condenses to water. And likewise, when you're freezing liquid water to ice, heat is taken out of water, and therefore it freezes into ice. In that case, right, when heat is removed or taken out, that's when you use Q is equal to negative ml. Okay, so the plus or negative sign there just indicates whether heat is being added for the plus sign, or heat is being removed for the negative sign. Okay. All right. An interesting thing to note here is that in this equation, Q is equal to ml, it does not contain anything about temperature, right? So you don't see any temperature change when you're doing a phase change. And so sometimes latent heat is also called hidden heat. Okay. Because you cannot really measure a change in temperature of the object. The object is just changing phase, and that therefore tells you that when an object changes phase, its temperature doesn't change. Okay? And all of the heat that you put into that material goes into changing its phase. Okay? So if we look, maybe it's easier to understand that concept by looking at it graphically. So you have here the graphical representation of the temperature of ice as it goes from ice to water to steam. Okay, so the x-axis here gives us the amount of heat added. So this is Q. Okay. And the y-axis tells us the temperature of the material as you are adding heat to the material. So that's temperature T. Okay, so ice is solid form of water. So ice can have a very, very low temperature. So say, for example, we started from negative 40 degrees Celsius for the temperature of ice. If you heat up ice will not melt immediately. Okay. So notice that sometimes you need to, if you take out ice from the freezer and leave it on the counter, it will take some time for that ice to melt, right? So the heat that you add to the ice will actually go into raising the temperature of that ice until 0 degrees Celsius. Okay. So notice here, heat added is about 20 kilocalories. So the heat that you add to the ice will go into changing the temperature of the ice. Notice how the temperature goes from negative 40 up to 0 degrees Celsius. Okay. So the heat added goes to changing the temperature up to 0 degrees Celsius. When it reaches 0 degrees Celsius, the ice starts to melt. Okay. And so you have there ice starting to melt. So you have a combination of liquid water and solid ice. So this 0 degrees Celsius is called is the melting point. 0 degrees Celsius is the melting point of ice, because at 0 degrees Celsius, the ice starts to melt and you have water and ice together. So So this blue section is when ice is starting to melt. Any heat that is added to the melting ice goes into melting the ice, converting that to water. So notice how the temperature does not change. It's the same. It's always still 0 degrees Celsius while ice is being melted to water, right? Okay, because any heat added during melting goes into the melting process and it doesn't influence the temperature of the melting ice. So if you want to maintain the temperature at 0 degrees Celsius, you need to combine ice with water. Once all of the ice have melted, okay, and you only have water, so it's all just purely water, any heat that's added to the water again goes into the change in temperature of the water. So notice how the temperature of the water initially at 0 degrees Celsius, when all of the ice have melted, starts to increase until it reaches about 100 degrees Celsius. Once it reaches 100 degrees Celsius, water starts to boil. Okay, so 100 degrees Celsius is the boiling point of water. Okay, and as water starts to boil, you're now changing phase from liquid to gas. So you have water and steam existing at the same time during boiling. Okay, and any heat that's added to the material goes into boiling the water and changing that into steam. So again, notice how when you have a phase change, the temperature stays the same because any heat that's added goes into the change of phase process, the process of changing from liquid to steam. Once all of the water has boiled out and you're only just having steam, that's when you again have this change in temperature. So any heat added to steam goes into changing the temperature of the steam. Okay. Right, so you have here two phase changes, melting and boiling. Notice that when you're changing phase, you have two phases that are coexisting. During melting, you have both liquid water and solid ice. During boiling, you have both liquid water and gaseous steam. Okay. So during phase change, you have these two phases together. And when you have just a single phase, like just only solid ice or only liquid water or only liquid gas, then you have this change in temperature as a result of heat being added to the system. So in terms of equations to use, okay, when you're undergoing phase change, so this was the boiling, which is the water changing phase from liquid to gas, and this is the melting, which is also a phase change with water changing phase from liquid to with ice changing phase from solid to liquid. Notice how during the phase change you use the equation Q is equal to mass times the latent heat. Okay. And when you only have a single phase that's existing, then you use Q is equal to MC delta T. Because then if you have a single phase that's existing, any heat that's added goes into the change in temperature delta T. Right. So that's how you know when to use Q equals MC delta T and when to use Q is equal to ML. Right. When you have a single phase, like only all the material is only solid or only liquid or only gas, then you use Q is equal to mc delta T, because the heat added goes into changing the temperature. But when you have two phases that are coexisting, like water and steam together, or water and ice together, then you should use Q is equal to ml, because any heat that's added goes into changing the phase of that material. All right. Okay, now let's look at an example of combining the change Q is equal to ml and Q is equal to mc delta T, and knowing when to use them. So steam burn is more dangerous than a burn from water at 100 degrees Celsius. Okay? And this is really true. So be careful with steam. And this example just gives us a numerical point of view of why steam is more dangerous than boiling water. So initially, steam is at 100 degrees Celsius, and then that steam touches the skin. The skin temperature is at 36.5 degrees Celsius. We want to calculate how much heat is transferred to the body as a result of 1 gram of steam cooling down from 100 degrees Celsius to 36.5 degrees Celsius. And we have here just the constant numbers. The latent heat of vaporization for water, that's when it goes from liquid to gas, is given here, and the specific heat of water is also given. So latent heat, that means L. L subscript V, vaporization. Okay, so just like any worded problem, let's write down what's given. So what do we know? So the mass, 1 gram of steam, mass of steam, 1 gram. We convert that again to base units, kilograms. So going from gram to kilogram, we divide by 1,000. So the mass of the steam will be equal to 0.001 kilograms. Okay, the temperatures, initially the steam is 100 degrees Celsius, then it cools down to 36.5 degrees Celsius. So the initial temperature is 100 degrees Celsius. Okay, and the final temperature is equal to 36.5 degrees Celsius. So notice some of the specific heat capacity is in Kelvin in verse 1. And our temperatures are given in degrees Celsius. But we've seen last time that when we're doing difference in temperature or change in temperature, it doesn't matter whether we're doing it in Celsius or Kelvin. So notice that Q is equal to mc delta T. C here is given in Kelvin. But when you're doing delta T, it doesn't matter whether you're in Celsius or Kelvin. So you can leave the initial and final temperatures in Celsius. Okay. So when you get the change in temperature, it doesn't really matter whether you did it in Kelvin or Celsius. So we'll leave it at that. Right, but we can get the change in temperature here. Final minus the initial temperature, 100 degrees minus 36.5 gives us a change in temperature of negative 63.5 degrees Celsius, which is also equal to negative 63.5 Kelvin. Right. Okay, latent heat of vaporization is given 22.6 times 10 to the 5 joules per kilogram, and the specific heat is 4186 joules per kilogram per Kelvin. Right, so this is all that we're given, you've just written it down. But now let's analyze the problem. So it says you have steam. It cools from 100 degrees Celsius to 36.5 degrees Celsius. So looking at our illustration again here, so steam, 100 degrees Celsius right here. So we start here, steam at 100 degrees Celsius. Okay, so before steam can cool down to 36.5, so the final temperature is 36.5, which is around here. So this is around 36.5 degrees Celsius. So before steam can cool down to 36.5 degrees Celsius, notice how steam needs to condense to water first, right? So you need So you need to condense this 100 degrees Celsius steam to water. And after it has condensed to purely water, that's when it can go down in temperature to 36.5 degrees Celsius, right? So it's not as simple as just going 100 degrees Celsius minus 36.5 degrees Celsius and using Q equals MC delta T, because you also have to consider this phase change of steam converting to water before you consider this change in temperature from 100 degrees Celsius to 36.5 degrees Celsius. Okay, so it means it's a two-step process. So first, energy is released. When steam condenses to water. Okay, so it condenses to water on the skin. So this is that first part, the phase change. Okay, that means you have a phase change here. Okay, and then second, after the phase change, you have the second stage where the condensed steam, the condensed steam, which is essentially water, cools down to, so the water cools down to 36.5 degrees Celsius. Okay, so that's that part here. So it's a two-step process. First, we need to calculate the energy released during phase change and the energy released when water cools down to 36.5 degrees Celsius. All right, so conceptually, that's what's happening. In terms of equations, so phase change, you have Q equals ML, but then energy is released. So you should have minus, Q equals minus ML for the release of energy. And here, for the second phase, you have Q is equal to MC delta T as the temperature of the water cools down to 36.5 degrees Celsius on the skin. Right, so we have now those two equations, and it's a two-step process. All right, so just before we proceed to solving this with numbers, does this analysis make sense? So just making sure that we understand what's going on. Okay, all right. Good, I can see thumbs up there. So let's proceed. So let's do the first process, energy being released as steam condenses to water. So Q is equal to minus ML we've already written down what's given. The mass of the steam that's being condensed is 0.001 kilograms times the latent heat of vaporization, which is a constant number for steam converting to water. Right. So just doing the calculation, you have negative 2,260 joules for the energy released as steam condenses to water. And then for the second phase, you have water cooling down to the body temperature. So that will be Q is equal to MC delta T. Right, so the mass, it's still the same. So we assume that the steam has a mass of 0.001, right? So when it condenses to water, we can assume that the mass of the water is also 0.001 kilograms. So the mass of the water that will cool down will also be 0.001 kilograms times the specific heat capacity of water, which was given in the problem to be 4186. Times the change in temperature, which we've calculated earlier, negative 63.5 Kelvin, or it's also negative 63.5 degrees Celsius. And carrying out all the calculations in your calculator gives you negative 266 joules as the energy released when cooling down. Energy released to cool down and energy released to condense. Okay. So the total energy released to the skin will be the sum of the two, negative 2260 plus negative 266 will give you negative 2526 joules. Okay, so that's the total energy that's released to the skin. First, the steam had to condense, releasing this much energy, and then the condensed water needed to cool down, releasing this much energy. So the total energy absorbed by the skin, is just the positive number of the energy released by the steam, right? Because we've seen earlier that the energy lost by one system, the heat lost by one system, one material, the heat lost by one material is equal to the heat gained by the other material. Okay? So the heat released by the steam will be equal to the heat absorbed by the skin, but the signs are just opposite. The negative one meaning heat was released, while the positive sign means heat was absorbed or gained, or heat was added to that material. Okay. Right, so here you can see why steam burn is really more dangerous, because the heat released during condensation, the heat released when steam converted to water, is so much bigger. It's about 100 times bigger than the heat that's released by just purely hot water cooling down on the skin, right? So here we can clearly see by comparing the numbers for the amount of heat absorbed by the skin, that the steam is really more dangerous than just purely boiling water. All right, any question to the solution to this problem, or if it makes sense, then some confirmation that we're okay and thumbs up would be good. Yeah. Are we happy with this solution? Yep. All right. Good. Okay, and so that wraps up our lecture for today. We looked at heat. We've learned that heat is the energy that's transferred from a hot material to a cold material. And the transfer of heat changes could change the temperature of the material. Different materials have different specific heats, and the lower the specific heat, the easier it is to change the temperature of that material. The amount of heat transferred can be calculated using this equation, where delta T is the change in temperature. Sometimes the heat added to the material causes it to change phase, and therefore the heat is specified by the latent heat of the material, indicating the phase change in the material. And if you start from one phase like gas and end up on a second phase like liquid, then you have to go through the process like we did in the example of the steam burn, where you need to condense the steam first before doing the change in temperature of the water. All right, but essentially this first equation is when you only have one phase that's existing and therefore its temperature will change. And the second equation, you use that during phase change, where you have two phases that are coexisting, for example, liquid and solid at the same time during melting, or gas and liquid at the same time during boiling. All right. Yeah, so that ends the lecture, and I'll just